One of the things that always fascinates me about forest management planning is how complex the entire system is. Forest management planning has to consider everything from wildfire risk to insect infestations, wildlife habitat, and of course, very naturally, the health of our water systems. So I was really excited today to be joined by Dr. Uldis Silins, a professor of Forest Hydrology at the University of Alberta. And he joined me to share all about the research that he's doing in Alberta to understand healthy water systems and what's impacting them. Really excited to share this episode with you today. Let's get into it. Okay, so Dr. Silins, really excited to have you on the podcast with me today. Could you just firstly start by sharing a little bit about your role with the U of A and the work that you do in hydrology?
Sure, absolutely. Well, first of all, pleasure to be here. Thank you so much for the invitation. Yeah, I am a professor of forest hydrology at the University of Alberta, where I teach water resources course, hydrology courses, watershed management courses, and then, of course, as a part of that role, I do a lot of research.
Yeah. How long have you been teaching at U of A?
Oh, geez. Late 90s. It feels like 173 years ago. So late 90s. And so the research itself, of course, started at the same time. In the early part of my career, I did a lot of research on just the role of forests as modifiers of water cycling in forested environments, both in boreal environments and in montane and mountainous environments.
And was this interest sparked maybe because you began your career as a forester, or like where did this kind of connection come from?
Some of my earlier summer jobs were in forestry, and one of them in particular was with the Watershed Management Branch, which we had at that time with the Provincial Forest Service at the time. And so I did that work for a couple of years, and that really sparked my interest in water resources in general and forest hydrology specifically.
And talk to me about, like, what is it about water that you are so fascinated by? What are the problems that you want to solve, the questions that you want to answer? Like, what was that early on, and what is that for you now?
I think it's a perfect example of a perfectly renewable resource that, because we're not really that involved in water cycling, and we kind of sit back and water cycling just kind of happens. And we're certainly the beneficiaries of that in terms of water supplies, in terms of provision of clean water for a whole bunch of different uses. But we don't play a very active role in it. And so it was the recognition, I think, early on that our forests play a really super critical role in water cycling. In Alberta in particular, most of the water that's produced in the province is produced from the forested part of the environment, particularly the east slopes of the Rockies, but also in the boreal regions as well. And so forests, in terms of cycling, provision of water, play a really important role. And so then disturbances within those forests also have the potential to modify that cycling. On some other sides, undisturbed forests probably produce what we would consider the best quality water. But water quality really varies, so it's when you have big rainstorms, big snowpacks, big melt events, water quality can be deteriorated quite quickly. And so water quality goes everywhere from really super clear, gin clear water to the river's running mud. And that can be from an undisturbed system. And then, of course, management, human influences. So it's not just managing those landscapes, but that's a whole range of human influences can affect that. So I think that was the thing that really motivated me to get interested in water cycling and forest hydrology in particular.
I mean, it is fascinating. And just as humans, of course, we all need water to live. It's the lifeblood of really everything here. I'm curious if you can talk a little bit about as well to like water availability or the amount of water that we have. You talked about how forests are really one of the most important factors in where water is. And I think Alberta is somewhere over 60% forested, lots of that, the boreal in the north. Would that influence the patterns of drought that we've seen, maybe like in southern Alberta a lot? I know last summer there was, of course, drought in northern Alberta, so there was a little bit of a change there. But Is that something you can speak to?
Sure. So the lion's share of the water is really produced from these forested environments. And we look at how our rivers flow in Alberta. Most of our rivers are flowing from the west, from the Rocky Mountain Front Range, easterly. And then a lot of them are flowing north.
Yeah.
So if we think about where people live in the province and where the demand for water is high, and this is kind of a moving target as well, because water demand has really shifted over the last quite a few decades. But the forests play a huge role in terms of the provision of flow, even though the use of that water by Alberta society, towns, cities, industries, user organizations, is quite a ways downstream. So when we talk about, going back to your question, if we look at the bigger rivers in the province, with the exception perhaps of the Peace River, which originates in British Columbia, but if we're looking at the Bow, the Oldman, the North Saskatchewan, all of those larger rivers, probably 80%, if not more, of the pickup of flow in those rivers happens in the east slopes, the forested east slopes. But then, of course, the river is flowing down through the settled parts of the region. So the settled parts of our province, the cities, the towns, the industries are really reliant on water that originates from these forested systems.
Yeah, absolutely. I mean, really, that's where the demand is, right? That makes a lot of sense.
Yeah.
So one of the reasons that, for me, I'm really excited to be able to have you on the show and to talk about water in a bigger context than we've ever really talked about on Forestry Talks is really because it's such an important component when we think about forest management planning. I mean, forest management plans, there's a lot of different values that are covered off in those, but water, the health of water systems, buffers, all of those are a key component of it. As a professor of hydrology, I'm sure you're sharing lots about the importance of water, how to think about water, how to manage forests and maybe buffers and those considerations for water. So maybe could you share a little bit about your work as a professor and what you share with students about how to think about water?
I'm going to approach that from the perspective of my broader mindset in how my research is tied in to that broader question.
Yeah.
So there's all kinds of, when it comes to watershed management, forest practices, there are all kinds of questions about what are the best management practices that should be done for protection of water resources. And so that's where things like riparian reserves, buffers, those come in. How big should the buffer be? What should the conditions be? How do we define the riparian zone? There's a million operational questions around control of erosion off road surfaces and cut slopes and fill slopes and ditches and all of that stuff. And so there's a million of those questions.
Yeah.
My work has maybe started more in that kind of fine scale questions, but I would say about 25 or 30 years ago, I started doing broader catchment scale research. And it was at that time that I really took on some of the broader problems or the broader questions that were outstanding at the time. How does disturbance in general, and those disturbances, whether those are anthropogenic disturbances, forest harvesting, different forest harvesting strategies, natural disturbances, wildfire, mountain pine beetle, disturbance events like flooding, or disturbance events that are compound. So we may have an environment that's harvested, and 10 years later, all of a sudden we have a really big flood event, which can be considered a disturbance event in of itself. And so there's a whole bunch of questions around, well, we've got one disturbance and we layer another disturbance over top of that.
Yeah.
Maybe even a third.
Right.
How do those occurrences affect water resources? Very broadly, at the time I started the broader catchment scale research, there was a ton of questions around wildfire.
Yes, of course.
And so those questions, while there's had been some research work done on catchment scale response to wildfires, at that time, and I'm talking 25 years ago, there was comparatively little knowledge of how wildfire-affected water
Right.
resources. Our timing was fantastic because we started working on the Lost Creek wildfire. And, if you think back, the Lost Creek wildfire in 2003 was right around the time the forestry sector was just starting to think, something might be changing with wildfire regimes. We didn't know it yet. And really, if we really went back, it was probably the Virginia Hill fire in 1998 or 99. And then, it's like the frog in the pot of warm water. Fire regimes were probably changing at that time, but we really didn't have the evidentiary basis to say, yes, in fact, something's different today than it used to be. It's talking to firefighters, old experienced firefighters, going, I've never experienced this kind of a thing before in my whole career. And so it was a whole bunch of those things. So that's a long discussion that feeds back to the basic question. Not only did we not know a lot about how wildfire affected watershed processes, and it was not because we were particularly clever. It was just, we were just lucky. That's when we started the work.
Yeah.
And so it was at the same kind of time when other research teams worldwide in fire-affected regions, Australia, Southwest United States, Western United States, started doing a lot more work on wildfire impacts to watershed processes. At the same time, we started doing this work here in Alberta, in Alberta Rockies. And we interacted with many of those scientists. We'd meet at meetings. I had lots of them come to Alberta. We've gone to other places in the world, spent a lot of time in Colorado with United States Geological Survey scientists. And we spent a lot of time asking some interesting questions. Why do you see what you see in your part of the world, but we never see that in our part of the world?
Interesting.
And because, the research after 25 years has really shown that while there's some effects of wildfire on watershed function that are somewhat common, there's a lot of differences.
Interesting.
And so we see things in Alberta that, say, our colleagues in Colorado don't see.
Can you
And
give
vice
some
versa.
examples of that?
Sure.
Yeah,
sure.
that's fascinating.
I'll use the example of one of the times I was in Colorado. It was, I think, around Estes Park around Boulder. Anyway, it doesn't matter. There was a wildfire there, and so we were touring this wildfire, and I was taking a look at the burn landscape and taking a look at some of the erosion. And I'd been thinking, we'd been working on this for quite some time, but I was looking at the burnt forest around me, and they were describing this as all high severity burn. And I was thinking of it from an Alberta context, and didn't say it at the time, but I was thinking, this is a moderately low intensity affair from my perspective.
Yeah.
Right? Thinking about Alberta wildfires.
Yeah.
Where we've got closed canopies. We've got, same forest type.
Yeah.
Lodgepole pine. We don't have some of the other species, but maybe not, their forest may be more open and that sort of stuff. And so looking at what they would consider high severity was basically crown scorch.
Okay.
And so, whereas, high severity in our part of the world, well, there's nothing left. The bark has blown off the trees.
Yeah. The soil is impacted.
Exactly.
A forest will come back.
There's no organic material left on the top of the soils at all. Yet, at the base of all of the hill slopes in Colorado, there was a debris fan from erosion. And it got us starting to think about the importance of the geologic settings. So in Colorado, it's all metamorphic rock. It's basically disintegrating bedrock, disintegrating granitic bedrock. So it's just weathering.
Yeah.
And it weathers to, granitic bedrock weathers to very coarse particulate matter. In Alberta, by contrast, we've got a sedimentary-based geology. So it's limestones, it's dolomites, but then it's marine shales and a number of these kind of sedimentary deposits that when they weather to really fine-grained material. And moreover, our landscapes have been glaciated 4 times.
Right.
20,000 years ago the last time. What that means is we have a huge supply of fine-grained particulate sediments at the surface. And so the difference between the two, because that's kind of the back of the explanation, but the difference between the two is in Colorado, they may have slightly more severe thunderstorms than us, but in Colorado, they get a good rainstorm, they have severe erosion, severe erosion. It moves a lot of material, creates debris flows. Some of these can be really catastrophic. There's examples where towns have been buried and people have been killed in these debris flows. Just a tremendous amount of erosion. But 2 or 3 years later, there's not much happening anymore. In Alberta, we've never observed that in 25 years of studying multiple wildfires in Alberta.
Yeah.
So because our sedimentary geology tends to be fine-grained, so it means that we don't have these big catastrophic emergency sediment erosion events that damage infrastructure, but we have a sediment signature, a sediment runoff signature that just doesn't end.
Oh, okay.
So as an example, we studied water quality after the Lost Creek wildfire, multiple burn catchments that were burned and then later salvage logged. And we saw sediment production going up and down year after year, always much higher than unburned reference watersheds. That variability is just driven mostly by wet years, dry years with big precipitation events or big snowpacks. And so what we were observing really was the effect of climate and weather on that. But you might have a very low sediment production year, and it's followed by another year when you've got a 30-fold or a 40-fold higher sediment production. It's really huge impacts on sediment. And it lasted for over a decade. So people would ask, why did you study the Lost Creek fire for 11 years in that particular case? And it was, quite frankly, because for many of the impacts, we saw no evidence of any hydrologic recovery after over a decade of study. And so we could have continued to do that work, and we're still working in that area. And we have revisited the Lost Creek fire. But so really coming back to the initial question was that it's hard to generalize those effects across different regions worldwide, partly because of the geology, partly because of the climate, partly because of all of these other things. And so there's a tendency for people to talk about those effects as if they're generic, but they're really not. Some of them are, but most of them, and the ones that matter, how big is the impacts, how long did they last, what aspects of the ecosystem are affected, those are really specific to the region. So we had, for instance, a sediment signature that was and sediment in particular is very strongly associated with phosphorus.
Okay.
Phosphorus, so if you've got high sediment production, you're going to have high phosphorus production. Phosphorus is the limiting nutrient in regulating stream ecology.
Oh, okay. So impacts to riparian health then.
Well, beyond riparian health, even just stream health. So you have, if you think of these mountain streams, they're, picture that in your mind. You get all these rocks are nice and clear, the water's gin clear. The productivity in that stream is limited by how much phosphorus is in there. You put a tiny little bit of phosphorus in there, and all of a sudden the system responds because it's so nutrient poor. And so how does it respond? It responds by primary productivity. In mountain streams, that'll be algal productivity and biofilms and in a lot of these things. And these are one of the things we saw immediately after the fire. These streams became absolutely choked with algae.
Oh, okay. Where
unburned reference watersheds, of course, it's the same thing. Nice clean rocks and all that's kind of the mountain stream that you picture in your mind. Yeah. After a wildfire, they were just choked with algae. And they remain that way for a long time. I'm a hydrologist, so, really studying water cycling, studying stream flow, studying water quality. Well, some of those changes were so dramatic. I'm like, okay, we have to measure some of this other stuff. So we had to sample the algae. We had to sample the invertebrates. We had to sample fish. And so we did a bit of bug squeezing and a bit of fish squeezing, afterwards, just because we had to put all this work in context.
Yeah.
And so what we saw, big picture, was, and this is quite different than you might see in some other landscapes. In Alberta, the wildfires, the mountain wildfires, produced a really strong sediment signature that produced a strong phosphorus signature. That in turn produced elevated primary productivity, algae plant growth. Mm-hmm. That in turn was food for the invertebrates that live in the stream. And we saw huge increases in the density of those invertebrates. And those, of course, are food for fish.
Right.
And so, lo and behold, we found an increase in productivity, growth rate of fish in some of these burned streams.
Interesting.
So in hindsight, it was not super surprising, but nobody had observed that before. Mm-hmm. It's a classic bottom-up trophic cascade. The fire affects sediment production, it affects phosphorus production, that affects the ecosystem across at least 4 rungs on the trophic ladder.
Yeah.
And so that was Lost Creek Fire. We then studied other fires, probably most similarly the Keno Mountain Fire after the 2017 big fire there.
And just really quickly to clarify, because I'm a newbie in this space, really and truly. So the sediment that we're talking about in the water after wildfire, is this coming from ash that's falling into the water? What's creating this?
So after a fire, you are going to have a lot of burnt material.
Yeah.
Burnt ash, burnt, organic material on the surface. And so a lot of that ash does get washed into the stream. A lot of it will stay on the forest floor as well. Mm-hmm. And so there's a legacy for that ash. It's not really driving what you would consider sediment. It's driving other aspects of water quality that are important. It's really driving organic carbon, because it's organic material, and the fire transforms the nature of the organic carbon. And so there's a lot of things that happen after the fire in terms of the condition of the organic carbon, the condition it's in when it gets to the stream, what the impacts of that are on the ecosystem, and some of the downstream impacts. For example, organic carbon is one of the big drivers of drinking water treatment processes. So if you back it away, and we've been working with drinking water treatment purveyors and drinking water treatment scientists. So one of the things people are concerned about after a wildfire is how is our drinking water affected? Mm-hmm. And at a very high level, the movement of mineral sediments, fine particulate sediments that drive turbidity, which is really a measure of optical clarity.
Okay.
So it's turbidity and dissolved organic carbon, which is the primary drivers of water treatment. So they're the ones that produce the challenges.
Right. Okay.
And so fires do transform the chemical condition of that organic carbon.
So it makes the process of refining that for drinking purposes probably a little bit more complex. I know that's out of your space.
No, that's actually, you put it just perfectly.
Yeah.
So people are concerned about, will we even have drinking water? Will our drinking water plants cack out or something? The reality is exactly as you put it. It makes it more challenging.
Yeah.
It just means that the drinking water treatment engineers, the operators, have to find a couple of new gears in terms of in terms of dealing with a post-fire environment.
They just have to work a little harder right now.
Right. But back to your original question, sediment, on the other hand, is the mineral soil. After the organic material's burned away, you've got a bunch of mineral soil that's exposed. Mm-hmm. And so sediment is really the typical total suspended solids.
Yeah.
Well, mineral sediments is basically the soil. And so you've got large particles, small particles, all those things. So it is then basically erosion and transport of those mineral sediments from burned landscapes down into the streams.
I see.
Once they get into the streams, some of those sediment, sediments settle, and the next time flows come up, they get re-eroded. So you've got a number of different sources for these sediments. But
so where the trees and the roots and everything would have been holding all of that material in place, when a fire comes through, it essentially loosens things up and makes it more likely
and
to...
the forest floor in particular, the
Yeah.
organic material in the forest floor plays a huge role in buffering the mineral sediments from raindrop impact.
Gotcha.
Or snow melt,
Yeah.
the consequences of snow melt. Yeah.
So something that I thought was really, interesting in your work, you talked about how forestry today is not the forestry that it was, 30, 40 some years ago. And I think perhaps buffers play a really important role in that. Could you talk a little bit about maybe your observations for how the way that we manage forests, how forest harvesting occurs, and how that considers water in a way today that is maybe different from what happened several decades ago?
I'm going to sidestep your question just a tiny
Sounds
bit, if
good.
that's okay. So I am going to address your question, but not in the way I think you intended,
By all
perhaps.
means.
So one of the things after we'd been doing, and we're still doing this wildfire research, we had the opportunity to do a really comprehensive logging study. And so there, two of the watersheds that served as the unburned reference watersheds for the Lost Creek fire. And again, we studied that fire for 11 years. So those two watersheds, right side by side, were calibrated to one to another over an 11-year period. So you've got flow in one related to flow in the other, water quality in one related to water quality in the other, the aquatic ecosystem health. All of those are calibrated side by side. One of the big challenges in forest watershed scale research is when there's a disturbance, and you're left comparing undisturbed watersheds to disturbed watersheds, there's a certain amount of assumption you have to put into saying, well, we're going to assume that the undisturbed watershed or the disturbed watershed would have been similar to the undisturbed watershed. Well, in this particular case, they call that a paired catchment study or a before-after controlled impact study. Effectively what it is studying two watersheds side by side prior to any disturbance, then having a disturbance affect one watershed, but not the other one.
Right.
And so you study them both before and after the disturbance of interest, and for many, 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 many years. And so what that does is it allows you to disentangle the effect of weather and climate on the behavior of the hydrologic behavior.
Yeah.
So, and it's really the dominant driver. The disturbance signature is always a much, much smaller signature underneath that huge range of variation produced by weather and climate. Back to, I am going to answer this question. I'm kind of taking you around.
Of course, the context is always helpful.
So we had the opportunity to do a paired catchment study because these two watersheds had been calibrated for 11 years. Nobody would ever do a study like that and invest 11 years in calibration. It just happened because it was part of the wildfire study. So that gave us an opportunity to then do a paired catchment study on different harvesting practices. Conventional practices, conventional of the day. So clear cutting with maybe green tree retention or distributed or patch retention, any number of different retention strategies. But then also look at some completely different harvest practices. So ones that may be considered by the forestry sector not particularly suitable for a lodgepole pine dominated mountain environment. So there's lots of questions about, well, why aren't you partial cutting? Well, okay, so let's have one of these catchments partial cut.
Yeah.
In a lodgepole pine system.
Yeah.
Okay. And then, so we've got a conventional clear cut, a partial cut system, and then we did a strip shelter wood system in another one. So this is where we really partnered with the provincial government. So this was a large long-term study that was driven by the provincial government, where we were really doing the research work. And so this is kind of our research on conventional harvesting is a little modified. It's a catchment scale look at some broad strategic harvest approaches.
And so what's the question that you're hoping to answer?
So the question really, the broad question was, how do these different disturbances compare? And it's not just that high. So for example, if you've got conventional clear cutting of lodgepole pine systems with retention, it's thought of as a moderately severe footprint. But in some ways, because you go in, you have a disturbance. There's still this patch retention, or whatever your retention strategy is. But at the end of the day, you've got one road in and one road out. Mm-hmm. And so, from a hydrologic and a water quality standpoint, there's really it's an unresolved problem. Is the impact from harvest disturbance largely from the harvesting itself, or is it from the linear network to go in and extract
road building?
Yeah. So is it the road?
Yeah.
And the road over time, the maintenance of the road.
Mm-hmm. Versus road reclamation. And was that measured?
We didn't measure it per se. But if we contrast that against, say, a partial cut, where it's truly a distributed partial cut, in this particular case, it was a mixture of single tree harvesting and group selection. Mm-hmm. But at a catchment scale, you can imagine the road network that's required to do a partial cut system is far, far more dense compared to a clear cut where you have one road in, one road out. You may have a network of skid trails coming to it. Partial cut system needs far higher road density
access.
And then a really high density of skid trails to be able to access and remove those. The shelterwood system we looked at was kind of halfway in between those. So at a very large scale, some of the big questions were, particularly with respect to water quality, how do those three very different harvest strategies compare in of themselves, given that they also come packaged with three very different, almost opposite road densities?
Right.
So the expectation might have been, well, you might expect some of the biggest impact from the clear-cut harvesting just in terms of intensity of the footprint. But on the flip side, if the source of the water quality deterioration is largely the road network, then paradoxically, you might expect some of the highest impacts from the partial cut system with a lower impact from the clear-cut system. And so the study was really set up that way to examine these very strategic approaches to harvesting, to answer these basic questions. And as it turns out, and it wasn't just from the perspective of how, there was questions about how is the hydrology affected from these three different harvest strategies? How is water quality affected? And then, how is ecosystem health of the stream affected? The other thing we did that's quite different, and it's rarely done, there's often lots of questions, well, how do those effects move downstream? The bulk of the research has historically focused on measuring these impacts from, the small catchment scale, and then doing a bunch of arm waving about, well, this is what the downstream effects are based on what we've seen in the, the water all flows downhill.
Yeah.
But the reality is, as you start moving downstream, watershed scale increases, and so it becomes a signal to noise ratio. And so the question is, it's almost like looking at a disturbed patch of ground, stepping into a helicopter and just taking the helicopter up and going, okay, that 1 square meter, now 100 square meters, now a hectare, a square kilometer, the disturbance footprint looks very different. So what we did is we, at the same time, set the study up to also look at what was happening downstream at increasing watershed scale. So at the fine scale, we're looking at the subcatchment scale.
This is a huge study.
Yeah, it's a massive
wow.
study. Millions and millions and millions of dollars are spent on this. It's a huge study. And so not only looking at what's happening at the subcatchment scale, but then going downstream within that system to the confluence with the Crow's Nest River in that particular case. So we go from 100 hectares or several hundred hectares at the smallest scale to 30,000, 40,000 hectares when you get to the Crow's Nest River scale. And so it was then looking at that full suite
Right.
of hydrologic changes across scales. So there's a lot buried in this particular
No
research.
kidding.
Yeah.
So at the end of the day, like, were you surprised by your findings?
Yeah. Yes and no. Some of the results in terms of the hydrology, and we're still doing that research, by the way.
Yeah.
That research is still ongoing. So some of the findings are pretty consistent with how we think we understand hydrology of those particular environments, but some results were really quite surprising. And so probably one of the ones that jumps out the most for certainly our partners, our government partners, and our industry partners. One of the things that happened after the harvesting was because we had 10 years of pre-disturbance data in both the reference and the logged watersheds, what we could show conclusively was after the harvesting, sediment production went down. And so this is not 1 year comparison.
Yeah.
This was given 11 years of pre-disturbance water quality data for both of them. We could show conclusively, year after year after year, after the harvesting, the sediment production went down.
Interesting.
And you're going, how is that possible?
Yeah.
I would have never thought about it. And to really, and of course, during the harvest,
Yeah.
the intention was to not do anything particularly unusual, kind of business as usual, but, adequate care and protection. So it was a broad suite of best management practices for erosion control that are typically were applied. And there's some of them probably had a bigger positive impact than others. But at the best, what that should have done is minimized the excess production of sediment from the harvesting.
Interesting.
But what we found was sediment production actually went down.
And any indication why, or is that to be answered yet?
So our best, and of course we didn't do the fine scale process research to really confirm this, but you already have an existing network of off-highway vehicle trails in there, cut lines, a number of those sorts of things.
Recreation,
And so the only thing that actually makes any sense is there were pre-existing sediment sources associated with some of that trail network that were pinched off
I see.
during the harvesting or the post-harvesting reclamation work. They reopened up all the main trails and a number of those things, but that's the only thing that makes sense, that there were, because we can disentangle climate from this. So it's not a climate signature. This is a pure sediment production signature. And so the only thing that makes sense is that there were sediment sources that were pinched off.
Interesting.
So that said, the water quality impacts, you can say, well, there was no impact, because that's really the take-home message. There was no impact. What it meant is we could not meaningfully, in terms of water quality, we could not meaningfully compare three fundamentally different strategic approaches to harvesting. Because water quality improved in all of them.
Fascinating.
What do you do with that?
Yeah.
There's not much you can do with that. The only thing you can really say is that the best management practices that were employed were absolutely effective in not only minimizing, but eliminating any potential adverse effects. There's still interesting hydrologic effects and all those kinds of things. But because there was no water quality effect on sediment, that meant there was no effect on phosphorus. There was no effect on the aquatic ecosystem. And then that meant that downstream, we did not see any propagation of those water quality signatures downstream.
Right.
And we monitored it. So the net result was, paradoxically, after logging, the Crow's Nest River below the confluence of Star Creek is ever so slightly cleaner than it was prior to logging. So,
well, there you go.
So again, what do you do with that? So about the only thing meaningful that can be said is it's certainly not in keeping with the objectives of the study, which was to provide more information. But it does confirm that best management practices can absolutely
working.
be effective. And when you say they are working, it's all about the devil's in the details.
Right.
So it means they have to be applied well.
Yes.
And sloppy imposition of best management practices is wasted money.
Yeah.
And probably has no effect. But where they're applied properly and with some care and attention, they're probably very effective.
Can you talk about, I'm assuming there are a number of listeners who probably don't know what those practices look like. Could you describe maybe some examples of what those properly applied best management practices are?
Well, simple things in terms of control of, say, let's talk about the road network. Simple things could be control of erosion off the running surface. Can't really do much about that. But that those sediments are eroded into the ditches, the cut slopes and cut slopes and fill slopes. And so that water collected in ditches, the longer it stays in the ditch and keeps running down slope, the more actually even erosion within the ditch is going to occur. So one of the simple best management practices are to get the water across the road as fast as you can. So from the upslope slide of the road, don't let the water stay in the ditch very long. You need a cross drain to move it into the downslope ditch, where you can run it off into the bush, where the water's going to infiltrate and the sediments are going to settle out. So it means controlling water on the road surface. That can be very, very difficult to do if you've got long running lengths. Like if you've got a long, steady grade.
Right.
There's limited opportunity to do that. So one of the things that the company that was doing this work did is they employed the use of rolling grades. And I don't know, many people haven't heard of those.
Probably not.
Yeah. And so really all that is making use of alternating favorable and adverse grades. So at a planning scale, the forestry sector would try to minimize the length of roads for all kinds of ecological reasons. We want to minimize the linear footprint. But detailed analysis of the terrain, if you go, well, okay, I want to capture, this is in the planning phase ahead of the harvesting, I want to capture the use of alternating adverse favorable grades if I'm going up valley.
Right.
So generally adverse grades, but I'm going to make use of alternating terrain, which means the road network could actually end up winding around a little more than it might otherwise do, because you're trying to make use of these adverse favorable grade switchovers. Every time the grade switches, that's another opportunity to get water across a ditch and across the road.
Right.
So the use of rolling grades, while it ends up producing a somewhat longer road length, provides far more ability to control water off of road running surfaces.
Wow.
Does that make sense?
It does.
Okay.
I'm like, the more, one of the things that just keeps blowing my mind is the more that I get to interact with folks that are part of this broader forest management ecosystem, the more I appreciate how complex the work is. Like, you yourself as a specialist in hydrology, we've talked about wildfire, we've talked about fish, we've talked about bugs, we talked about soil, we talked about rocks. Like, it's just, it's always, so
and
much bigger.
it's interesting because that's a counterintuitive idea. And it's paradoxical in terms of how we've always thought about it.
Yeah.
Let's minimize road length to minimize those impacts. But in fact here, and we're using road density, road length as proxy indicators of disturbance. When in fact done properly, you can actually produce, if you're using this rolling grades approach, you can really reduce the impact on water resources while increasing road length. Because that's the trade-off.
Which seems a paradox.
It's paradoxical.
Yeah.
Other things, just in terms of making sure that those cross drains are maintained, and then there's simple standard things, standard silt fence, those kinds of things.
Buffers.
Right. There are other things that can be done in terms of crossing, decommissioning, and a number of those things. And here's where the challenge comes in, because typically we leave those roads open for a period of years. You need to come in and do the silvicultural work and do all of that other kind of thing. But in this particular case, for this watershed, the decision was made to get in and get out as fast as possible.
To reclaim the road.
Yeah. So it was basically, the entire operation was done in 1 year.
Wow.
So the roads were put in
Yeah.
in January, and everything was pulled out by November
Wow.
that year. The brush piles were burned. The roads were all decommissioned.
a big job.
Not only just decommissioned and ripped, the side slopes were recontoured. Everything was done.
Yeah.
And so there's a whole lot of things that they're not outside of the scope of what's possible or what could be done, but they wouldn't necessarily affect an operational forest operation in, say, a working compartment or something over a 5-10 year period.
Yeah.
But I have no doubt that the decommissioning of that haul road, the decommissioning of some of the spur roads played a role in minimizing the water quality impacts.
Yeah.
Lots of questions about, can you do that everywhere? Well, you probably can't. But this is something that it might be able to be done in some particularly high value watersheds with, a great deal of concern. So there are possibilities. And again, this wasn't part of the research work. This was part of the operational imposition of those 30 different harvest strategies.
Yeah, the control, making sure those best practices were applied. And awesome. Well, Dr. Silins, this has been really, truly a fascinating conversation for me. I know we've gone through a few of your different research projects. We talked about, I think, I was going to call it Star Creek study, but it's...
That's one I've been talking about.
Okay, I know, but you were calling it the Lone Creek, or is the Lost...
Lost Creek was the wildfire.
Okay.
In the same area.
Lost Creek and this...
Yeah, and then the Keno Mountain Fire happened in 2017, further to the south, maybe about 40, 50 kilometers as the crow flies.
Okay.
So we had two fires that we studied in the same pile of rocks, more or less side by side, separated by, 15, 20 years. With largely similar impacts, but some interesting differences too.
Yeah.
Yeah.
It sounds like it. I mean, your research is just such an interesting body of work. And then even to your point about the geological differences, when you start looking outside of the province, how some of these questions are not answered the same way, I guess.
Or you can't generalize. You have to be cautious when you generalize.
Yeah. Fascinating.
Yeah.
Well, I've so enjoyed this conversation. I guess my last big question for you is, what kind of questions are you hoping to answer in your work in the next couple of years?
That's a great question. I think what we've started already towards the tail end of my career. Somebody asked me probably about 8-10 years ago, what do you see as the most significant and problematic challenge that we're facing with water resources in the province related to my field, related to disturbances and those sorts of things? And I hesitated to answer the question immediately because I didn't want to answer the question because it's not a good scientific question.
Okay.
It's fraught with uncertainty, which these don't make good scientific questions.
Right.
But truly speaking, there's kind of a whole field in hydrologic research that deals with cumulative impacts. So we talk about cumulative effects, and a lot of times people talk about that almost a cavalier conversation. Cumulative effects, yeah, it's a good idea. Let's do it that way. Let's study it. Well, the reality is it's exceedingly difficult to characterize cumulative effects. Easy to talk about. Almost impossible to do from a watershed perspective in particular. And so from that standpoint, my answer was cumulative watershed effects are probably one of the most challenging issues that we're struggling with and that we're likely to continue struggling with. And so we've been doing all this work in the Crow's Nest Pass region of southwest Alberta. And the Crow's Nest River is one of three main rivers making up the headwaters of the Oldman. We have the Upper Oldman to the north, we have the Crow's Nest River in the median part, and then the Castle River coming in from the south. Well, along the Crow's Nest Valley, we're going from a prairie agricultural, just a beautiful range country, to Front Range and kind of Continental Divide in about 25 kilometers. So we're going from an agricultural setting through a setting that has a whole series of communities. We have a highway running down the center. We have a whole series of communities with expanding municipal footprint. There's a tremendous amount of development pressure in that area. There's historic forestry, there's current ongoing forestry, there's historic coal minings, there's pressures on new coal mines, there is massively expanding recreational pressures in the area. There are a whole bunch of things happening in that watershed. And so getting back to your question, one of the things I decided in the back end of my career is to really, and we're not going to solve this problem, but it's going to be, how do we structurally approach this? Because we have all these overlapping disturbances. One's a cherry, one's a banana, one's a potato, and you can't compare to they're all very different, and they affect water resources in similar or different sorts of ways. And so what we are now 3 years into is a study of cumulative watershed impacts on the Crow's Nest River, really from the top of the Continental Divide to where the Crow's Nest River flows into the Old Man Reservoir.
Interesting.
And, we've had lots of meetings with producers and municipalities and those sorts of things. We've got a pristine, semi-pristine kind of mountain river there. We've got a wastewater treatment plant. We've got, we have all these things that are putting pressure on the river. And so at the end of the day, what we're seeing is very different sorts of impacts as we go from the top end to the bottom end, but sort of projecting forward towards the end of that in terms of, what does this mean in terms of economic development in that region? Our work is probably going to show that all of those human footprints are pretty important in different sorts of ways, and nobody's going to be scot-free on this one. It's going to be everything from recreational development, which is having significant impacts. It's going to be coal mining, some forestry, certainly the municipal footprint, and the expanding municipal footprint there is going to be a big player.
Right.
And then the agricultural sector, of course, continues to have significant impacts. And so those are all important to our economy, of course, but they all have differential impacts on water resources that we care about.
Yeah.
And it's important to be aware of that range of impacts. Not to identify a smoking gun, or not to, this producer sector is worse than this producer sector when it comes to that, but each one of them have challenges that can be dealt with. So that's kind of where we're still continuing to do the work on the Star Creek logging. We are just decommissioning the Keno Mountain wildfire sites. And we last year started going back to some of the Lost Creek sites. An interesting little bit to sort of end off on. I talked about an impact of the Lost Creek wildfire that lasted over 11 years, lasted over a decade. Well, we continued to see, just casually, those streams being impacted. We went back last year and did some low-level sampling and kind of resampled a bunch of stream invertebrates and stuff, and we are now showing that, just really preliminary analysis is showing that, yes, in fact, the impact of that fire on invertebrate communities is still very clearly detectable 21 years, 22 years after the wildfire.
No
so
kidding.
Very, very long-lasting effects, and one of my staff members is going to be presenting that work at European Geophysical Union here in March.
Fantastic.
In April.
Yeah, wow.
Yeah.
Well, sounds like there's a lot of still big questions ahead, so I really look forward to continuing to see your research and your work unfold and maybe getting some more answers.
Cool.
Awesome. Thank you so much. This has been amazing.
My pleasure.
Yeah. If you enjoyed this episode with Dr. Uldis Silins and you're curious to learn even more about the science that goes into forest management planning, check out one of our previous episodes where Dr. Amanda Schoonmaker joins me to talk all about the best practices for reforestation. And if you're curious to learn even more about forestry in Alberta, check out our website, albertaforestproducts.ca or loveabforest.ca. As always, I'm your host, Aspen Dudzic, and this is Forestry Talks.
This series is proudly produced by the team at Road 55. Road 55 creates content that connects. For more information, visit our website at road55.ca.